7 minutes ago, a headline dropped that quietly rewrote what we thought a computer could do, and almost nobody noticed it happening. While the world scrolled past another ordinary morning, engineers inside Google's quantum lab were staring at a result that took a machine the size of a chandelier and made it outrun the fastest supercomputer on Earth by 13,000 times. That is not a typo, and it is not a marketing exaggeration. 13,000 times faster on a task that would have taken a classical supercomputer more than 3 years to finish. Google's quantum chip did it in a matter of hours, and it did something even stranger than speed. It proved its own answer was real. This is the story of Willow, Google's quantum processor, and an algorithm called quantum echoes, and why the people who understand it best are calling it the first genuinely verifiable quantum advantage in history. To understand why that phrase matters, you have to understand what quantum computers have struggled with for years. Speed alone was never the hard part. Back in 2019, Google claimed something called quantum supremacy, showing that a quantum chip could solve a problem faster than any classical machine. Critics pointed out a real weakness. The problem it solved was essentially useless, a puzzle designed only to be hard, with no way to independently check the answer against anything meaningful. Quantum computers are famously fragile. Qubits, the building blocks of quantum information, are so sensitive that a stray vibration or a whisper of heat can corrupt them. For years, that fragility meant results were fast but unreliable, powerful but unprovable. Nobody could fully trust what the machine said it found. Think of it like this. Imagine someone hands you a calculator that claims to have solved an equation no human has ever solved. But the calculator is also known to glitch constantly, and there is no way to double-check its work. Would you trust the answer, or would you assume it just malfunctioned in a way that happened to look impressive? That has been the central problem haunting quantum computing since the very beginning. Every few years, another lab announces another milestone, another chip, another claim of supremacy, and every time, skeptics ask the same question. Can anyone actually verify this, or are we just trusting the machine's word for it? Google has not been alone in this race either. IBM has pushed its own roadmap of increasingly large quantum processors, chasing thousands of qubits. Chinese research teams have published their own supremacy claims using photonic quantum systems. Startups all over the world, from small labs to well-funded companies working with trapped ions and neutral atoms, have been racing toward the same finish line, each claiming their approach is the one that will scale first. But raw qubit count was never the whole story, because more qubits without reliable error correction just means more noise, more fragility, more results nobody can fully trust. What made this particular announcement different is that it did not lean on scale alone. It leaned on proof. Quantum echoes changes that equation. The algorithm works almost like sonar, sending a carefully shaped signal of information into the quantum system, then reversing it and listening for the echo that bounces back. Scientists nudge one qubit in the middle of that process, a tiny perturbation, and then measure how the echo shifts because of it. That shift reveals something classical computers cannot efficiently calculate, a phenomenon called an out-of-time order correlator, which physicists use to study how information scrambles inside complex systems. Here's the part that should genuinely stop you. The result from Willow was not just fast, it was verifiable, meaning another quantum computer of similar quality could run the same experiment and get the same answer. That is the difference between a magic trick and a measurement. A magic trick impresses you once. A measurement can be checked, repeated, and trusted by scientists who were not even in the room when it happened. Google's own research leads describe this as the first time in history that a quantum computer ran a verifiable algorithm that surpassed the ability of supercomputers, not just outran them on a rigged test, but on something that could be cross-checked and confirmed. And the checking was brutal. Researchers spent roughly 10 years of combined human effort red teaming this result, throwing 9 different classical simulation strategies at it, trying to prove the quantum answer was wrong or replicable by ordinary computers. None of them could catch up. The gap held. To put that 10 years of red teaming in perspective, imagine an entire decade of a single person's working life spent doing nothing but trying to poke holes in one experiment. Now imagine that effort, compressed and distributed across a team, still walking away unable to break it. That is not a company patting itself on the back. That is closer to what scientific consensus looks like when it forms in real time. The physics itself is almost poetic once you sit with it. Out-of-time order correlators, the strange quantity at the heart of this experiment, were originally developed decades ago by physicists trying to understand chaos in nuclear systems. Later, the same mathematics turned out to describe something wild, the way information scrambles inside a black hole, one of the most extreme environments in the entire universe. So the same tool being used here to measure distances inside a molecule for drug discovery is mathematically related to tools physicists use to study the edge of a black hole's event horizon. That is the kind of detail that sounds like science fiction until you realize it is sitting in a peer-reviewed paper published in Nature. one of the most rigorously vetted scientific journals on the planet. Now here is where the story stops being an abstract physics flex and starts touching your actual life. This is not just about proving quantum computers are fast, it is about what fast, verifiable quantum computers can eventually be pointed at. In a separate experiment with researchers at UC Berkeley, the same quantum echoes approach was used on real organic molecules, essentially turning the quantum chip into what scientists are calling a molecular ruler. It measured structural distances inside molecules with a level of precision that could reshape how new drugs and advanced materials are designed, because before you can build a better medicine, you have to understand the exact shape of the molecule you are working with. That is not science fiction. That is chemistry research happening right now, powered by a machine that technically should not be able to outperform reality's best classical simulators, and yet it does. But speed and precision are only half of why this moment matters, because there is a darker thread running alongside it, and it involves artificial intelligence. Separately from the quantum echoes result, researchers connected to Google and a quantum computing startup published findings suggesting that AI is actively accelerating the timeline toward quantum computers powerful enough to break the encryption protecting the modern internet. Cybersecurity experts who reviewed the research did not respond calmly. One researcher at Cloudflare, a company that secures a significant chunk of global internet traffic, called the findings a real shock and said defenses would need to speed up considerably. Cloudflare has already moved its own internal deadline for quantum-resistant security forward, tightening its timeline to prepare for a world where today's encryption can be cracked. Think about what that actually means for a second. Every password you have ever typed, every bank transfer, every private message, all of it currently sits behind encryption that assumes breaking. It would take an ordinary computer longer than the age of the universe. Quantum computers threaten to erase that assumption. And according to this new research, artificial intelligence is not just along for the ride. It is actively shortening the runway. For years, the general advice from security experts was calm and measured. They said a cryptographically relevant quantum computer, one powerful enough to actually break widely used encryption, was likely a decade or more away. That timeline let governments, banks, and technology companies plan a slow, orderly transition to new quantum-resistant encryption standards, migrating systems gradually instead of scrambling under pressure. What this new research suggests is that the slow, orderly version of that plan may no longer be realistic, because artificial intelligence appears to be compressing years of trial and error into a fraction of the time. Instead of quantum researchers manually searching through possible algorithms the way scientists have for decades, AI systems are being used to search that space far more efficiently, surfacing promising approaches that a human team might have taken years to stumble onto. That is the same pattern we have seen AI cause in other fields, from drug discovery to protein folding, except this time the field being accelerated is the one guarding almost everything digital about your life. One of the researchers involved, who previously worked inside Google's own quantum division before leaving to co-found a new quantum startup, described using AI tools and seeing what he called crazy results strange enough that Google reportedly opened a new internal research push shortly afterward, focused specifically on AI-driven quantum discovery. This is the uncomfortable truth sitting underneath the celebration. The same week, the world is marveling at a machine solving physics problems 13,000 times faster than a supercomputer. Cybersecurity experts are quietly moving their doomsday clocks forward. Governments have not been sitting still either. Agencies responsible for national digital infrastructure have spent recent years pushing organizations to begin adopting post-quantum cryptography, encryption designed specifically to resist an attack from a future quantum machine. But adoption across the internet has been slow because migrating encryption on a global scale is expensive, complicated, and easy to postpone when the threat still feels theoretical. This new research is exactly the kind of development that turns a theoretical threat into an urgent one, the kind that forces boardrooms and government agencies to stop treating quantum-safe encryption as a someday problem. Google's own team frames this differently, of course. To them, quantum echoes is a stepping stone toward a future of error-corrected, large-scale quantum computers that could tackle problems humanity has never been able to touch, from new materials that could revolutionize batteries and clean energy, to modeling molecules for medicine we cannot yet imagine. They talk about black holes, about magnets, about the fundamental structure of nature itself, all becoming measurable in ways that were previously locked behind computational walls no classical machine could climb. And there is something genuinely thrilling about that vision. For decades, quantum computing lived mostly in theory papers and skeptical headlines, a technology that always seemed to be 5 years away from mattering, no matter which year you asked. Willow, and results like this one, are the first hard evidence that the 5-year horizon might finally be collapsing into the present. The chip itself used 65 of its 105 available qubits for the largest runs in this experiment, leaving real headroom for what comes next as engineers scale these systems further. Google has already opened proposals for outside researchers to gain early access to Willow, meaning this is not staying locked inside one lab. Universities, startups, and independent scientists are being invited to test what this hardware can actually do in the wild. That detail matters more than it sounds, because breakthroughs that stay locked in a single company's lab tend to remain curiosities. Breakthroughs that get handed to the wider scientific community tend to compound, fast, in directions nobody originally predicted. So where does that leave us? 7 minutes after a headline most people scrolled straight past. We are watching two timelines accelerate at once. One where quantum computers start solving real chemistry and material science problems that could reshape medicine and energy within our lifetimes. And another, quieter timeline where the same underlying technology, sharpened by artificial intelligence, is pushing the world's cybersecurity infrastructure toward a reckoning that most people have not even begun to plan for. Both of these are true at the same time. Both are unfolding right now, not in some distant speculative future, but in research papers published in the last few months, verified in Nature, scrutinized by outside experts, and confirmed through repeatable experiments rather than marketing slides. That is what makes this different from the last decade of quantum computing hype. This is not a company promising something someday. This is a peer-reviewed, independently checkable result sitting in front of the entire scientific community right now. The question is no longer whether quantum computers can eventually do something extraordinary. The question is how fast the rest of the world, our encryption, our institutions, our understanding, can catch up to what just happened inside a chip smaller than a dinner table. 7 minutes ago, that question got a lot more urgent, whether the world was ready to hear it or not. And if history is any guide, the moments that quietly slip past us, like this one, are usually the ones we end up looking back on and asking how we missed something this big while it was happening right in front of us.